Hi everyone, and welcome back to another video about using STK. This one in particular, I want to just highlight a recent work that we put together. So myself and my co-authors here, looking at coarse-grained models of cages. In particular, we use STK to build thousands of different cages by modifying the either ditopic, tritopic, or tetratopic angles. And so we take any cage, it has one of these building blocks with one angle, another building block with another angle, and we put them on all of their topologies. And we can compute their relative energies in this coarse-grained, very simple model. We can do this all very quickly. And then from that, we can map basically the two parameters, so these two angles, one for building block 1 and one for building block 2. We can map that into a cage space, or accessible topology space, where if you see a point with just a single color, it means only a single topology is stable, whatever this blue one represents. Or if you see a mixture, then you have a mixture of topologies that are stable, or there's the possibility that there are no stable topologies. So the concept here is that if you have two molecules that you want to form a cage from, and you know the two angles, you can pinpoint what cage is likely to form. And in this simple case, we have tried to make this process simpler or more user-friendly by providing an open database. So obviously the code is open source to do all of this, but also the database that contains all this information is open source, and I'll show this. There's also a mention of it in section S13 of the supporting information, but hopefully this video covers it much better. So the database is available on my website under self-sort maps. And if we actually I've used in this initial form, I've used a Notion database. Ideally, I would turn this into a web app that actually does a bit more than just containing the existing data. But for now, we can go to this topology data set in Notion, and there's some instructions here. But what I'll show you is that we have I'll just run through this very quickly. Basically, we have the three databases of either a ditopic building block plus tetratopic, a ditopic plus tritopic, or a tritopic plus tetratopic. So we'll just select one of these. We'll go ditopic plus tritopic, and normally the database should be unsorted and show everything. But you can see here we have these different columns. So these are the names of the cages, which is not too important to the average user. But the main properties are the tritopic angle, which is shown here. It's this angle in green. The ditopic angle, which is this angle in red. And then we have the stable topologies, which is green if there's only one stable topology, but you also have mixtures of topologies and so forth. And then we have some GitHub links to images of these cages at this point. So being a Notion database, you can sort it by particular properties, or you can filter it. So I like to filter for tetratopic angle of 90. And actually doing this reproduces the data in figure 2 of the paper. So this is all tetratopic, so square planar tetratopic building blocks as we increase the ditopic angle. And if we select one of these ditopic angles, or actually let's select a few of them, let's go 100, 135 and 155, and we look at these figures, we can see the cage structures from the coarse-grained models, and then their relative energies on the top. And so in this case, none of the cages are particularly stable, hence the energies are in red. But if we go to a different angle, for example, we see this cage is stable with an energy in blue, and at this angle here, we can see this cage is stable with an energy of 0.3. And we can now visualize the strain that exists in some of these other cages as a function of building block properties. So this is under development by me, but this is all currently open based on this paper. But as we hopefully publish more works, we'll see a better form of this database in the future. I wanted to introduce something that I've started using now that Lucas Turkani has developed, so STK's other developer. He's developed atomlite, which uses an SQLite database and provides a Python API for introducing molecules into that database. The quick start guide and the documentation is very thorough, as expected. One thing to note is that this tends to require Python 3.11. What I want to show in this video is just an example of using atomlite with STK molecules naturally. So I've taken an STK molecule directly from the documentation, this cage here, and I want to build this cage, add everything to a database, and then analyze the pore size of just the cage. So we start by defining an atomlite database and giving it a file name. So this will just create a file on your computer that contains the database. And what we'll see here is there'll be no entries. We will then build the cage in the normal way. And then we can use a list of atomlite entries to update the entries. We can also do db.add entries like so. Sorry, db.add entries. It would be the same, except the update entry handles if the molecule or entry is already present in the database. So an atomlite entry, we are going to take it from an RD-kit molecule. So atomlite provides that interface for handling molecules very well. We're going to provide a key. So this defines how you can look up the molecule in the database. We're going to use STK's toRD-kit molecule method to take our cage, turn it into an RD-kit molecule, and then atomlite can turn it into an atomlite molecule. And we're going to provide a property dictionary. So this can be any dictionary type in Python, and here we're just going to say it has a property of is building block, and this is either false or true. And so for the cage it is false, for the building blocks it is true. So if we now run this up to this input statement, we should see there are 0 entries. We build the cage, we add the 3 entries, there are 3 entries, so that's good. The next step is we can perform our computations on our database. So we can iterate through all of them with db.getEntries. And we can, if not building block, then analyze. So if the entry has properties is building block and that property is true, we are going to skip it basically. And if it's not, so therefore it's the cage, we are going to use STKO to compute its pore size. So we need to convert from an atomlite molecule, so entry.molecule. We need to convert that from JSON to an RD-kit molecule, which is what this line does. And then we can initialize an STK molecule from that with this line. And then being an STK molecule, we can pass that into an STKO method, so geometry analyzer dot get min centroid distance, and this will give us our pore size. We can then update the properties of the database by running db.updateProperties and providing the key for the molecule. We could have also done this in a slightly different way. We could have gone db entries keys equals cage, right? And that would have been the only key that we were interested in, but we may not always know that is the case. So we can run this, and the other thing I wanted to print out is just what the actual entry in the database looks like. So we have, for the building blocks, we have the entry, the key is BB1, the molecule is just a JSON of the atomic numbers, the bonds, the bond orders, and the conformer position matrices. This could actually be multiple conformers, but we only have one at this point, and then a dictionary of properties as prescribed. So it's relatively simple to read actually what your data looks like. And then if we go to the next line, for example, maybe much later on after you've done all the computations, you can run for entry and db.getEntries again, and you can just analyze entry.properties dictionary to get something, whatever you're interested in. But if we run that, you'll see cage is building block false. Pore size is 3.2 angstroms. And yeah, so that's it. Thank you very much for listening.